Hello and welcome, class, to our final section, our final part of Chapter 12, where thus far we've talked about liquids, we've talked about solids, but now it's time to bring Chapters 11 and 12 to a close by discussing phase diagrams, phase changes, heat exchanges as these phases pass from one to another. So in this final lecture of Chapter 12, we're going to be tying together Chapter 10 with enthalpies, Chapter 11 with our gases, Chapter 12 with our liquids and solids, all of this kind of like coming together. All right, so let's start with phase diagrams. So what a phase diagram is a representation of how the phase of a substance is going to depend on pressure and temperature. So in the graph that we have below, this is not an illustration of pressure versus temperature in the sense that pressure is dependent on temperature, but rather we can read this almost like a coordinate map. Right, so if we're reading like a treasure map and we're told XY coordinates, we can use that XY coordinate, to find where the treasure is hidden. Here, same kind of thing, only we're looking at how the phase of a material is dependent on the pressure and the temperature. We could see the pressure here specifically is listed in atmospheres. The temperature is in degrees Celsius. These units may change all depending on exactly what phase diagram you're looking at. So we can see that the pressure ranges from 0.1 atmospheres to 1,000 atmospheres on this particular diagram, and the temperature from -100 to +60 degrees Celsius, and this map corresponds specifically to carbon dioxide. So if we are looking at carbon dioxide at just 1 atmosphere of pressure and at room temperature, we can see that the point where these two coordinates meet is here, approximately squarely in the gas section of this phase diagram, meaning that carbon dioxide at 1 atmosphere of pressure and approximately room temperature will exist as a gas. All right, so if we want to know what other conditions are necessary for other phases of carbon dioxide to exist, all we have to do is look at the map. So carbon dioxide, for instance, at 1 atmosphere, regardless of the temperature, can only exist as a solid or as a gas. We can see at 1 atmosphere, this cross-section horizontally can only be found in this green and this kind of like peachish sections, meaning that carbon dioxide at ambient pressures cannot exist as a liquid. It's not that it's rare, it's that it physically can't exist. In order to get carbon dioxide as a liquid, even at its lowest pressure, it looks like we need to have approximately somewhere around like 5 atmospheres of pressure maybe, although this is a logarithmic scale, so it's kind of hard to tell. All right, and that alone would have to be at a temperature of around like -55 degrees Celsius. So we need some pretty extreme conditions to get carbon dioxide into its liquid phase. All right, so there are a couple of specific features of a phase diagram that we can observe. So I'm going to clean this slide up a little bit. All right, so just so we can more easily read these special points. First and foremost, we can see there is this point here in carbon dioxide's map or phase diagram labeled as the sublimation point. Now, carbon dioxide, because it cannot turn into a liquid at 1 atmosphere, doesn't have a boiling point that we would normally observe for things like water, let's say. Because it goes straight from solid to gas, it is going to undergo the process that is known as sublimation, and we'll talk a little bit more about what this quantitatively means later in the lecture. But suffice to say that the transformation from solid directly to gas is known as sublimation, and so carbon dioxide is going to have a sublimation point, and we can see that that occurs at -78 degrees Celsius. If we follow this line downwards, we can see where it intersects right here. All right, another feature of this map, which again I'm going to clean up because I just wrote right on top of it, is known as the triple point. The triple point of a material is exactly the pressure and the temperature where solid, liquid, and gas meet. So for carbon dioxide right here, we can see that this is going to correspond to a temperature of -57 degrees Celsius and a pressure over here of 5.1 atmospheres. All right, so this triple point How it would physically look is this sort of like amalgamation of solids steeped in liquid, sort of like ice water, only it would be carbon dioxide ice water, or like ice liquid, as well as there would be gas present. So it's like all three phases would be able to coexist at this point. All right, the third point or feature that we are going to discuss on this map of this phase diagram is here, known as the critical point. So the critical point of carbon dioxide occurs, we can see if we trace this dotted line down, is at 31 degrees Celsius, and all the way across is at 73 atmospheres of pressure. Now what the critical point signifies is that this is the point where the liquid and the gas phases sort of disappear, and we have this new phase known as a supercritical fluid. Now a supercritical fluid is an entirely new phase. It's not like the triple point where the solid, liquid, and gas coexist happily together. This is an entirely new phase. And what this phase looks like is that of a pure fluid. Both liquids and gases have what we call fluid properties. They're both able to spontaneously move, molecularly speaking, right? That's what gives liquids their flow and gases the ability to fill the chambers that they're in. A supercritical fluid holds a lot of the same properties as liquids and gases simultaneously. What it physically looks like is sort of like a condensing condensing gas. So you can kind of see wisps of liquids in the air, or almost like a liquid that has like the ability to superflow. So it visually looks sort of like a superposition or a superimposed version of liquids and gases, but it's not quite, it doesn't have the same phase boundary, the clear boundary that liquids do. And similarly, you can actually see it, so it's not the same kind of like permeable observation that you would make of a conventional gas. All right, so let's talk a little bit more about these critical fluids. So Thomas Andrews, a scientist who was working in the mid to late 1800s, he was one of the gas/fluid laws guys working along with Rudolf Clausius and Emil Clapeyron, was one of, if not the first scientist on record to observe critical fluids. And his observation of critical fluids was that the ordinary gaseous and the ordinary liquid states may be made to pass into one another by a series of gradations, meaning that you can't really tell the boundary between the liquid and the gas anymore. So gentle that the passage shall nowhere present any interruption or breach of continuity. In other words, it is all one phase. It is all one thing. And we can see in this illustration here a liquid that is turning into a critical fluid. So this line that we can see being drawn horizontally across here is where the liquid was originally poured into, like up to that line. And in the background, we can see the temperature, which is 29.2 degrees Celsius. So what is happening here is that we are varying the pressure, and as a result of the varying pressure, we can see that the volume of the liquid appears to be increasing a little bit. So what's happening here is that the density of the liquid is changing such that now the liquid needs to occupy more volume. And what we would eventually see in this video is that this boundary right here between the liquid and the gas would disappear. And suddenly we would have this kind of wispy appearance all throughout the chamber. And that is what a critical fluid looks like. So if you would like to see that, check it out for yourself. This picture right here is literally a thumbnail from a YouTube video. All you need to do is go onto YouTube. There are so many videos of supercritical fluids, particularly of, carbon dioxide and cyclohexane, or just hexanes in general. They're very, very common undergraduate demos to see what supercritical fluids look like to the naked eye. All right, but we are not going to be spending a lot of time actually observing supercritical fluids. We tend to leave the more thermodynamic / experimental observations of supercritical fluids for more of the upper divisional classes. So we're going to turn our attention to the more conventional phases that we have been talking about, the solids, the liquids, and the gases, and start discussing how the phases transition from one to the other, starting with the normal boiling point. So the normal boiling point because there can be different boiling points all depending on what pressure you're at, is defined as occurring specifically at 1 atmosphere of pressure. And as it turns out, the temperature at which the vapor pressure of your liquid equals 1 atmosphere is going to be that of the boiling point. So this is significant because the vapor pressure, as a reminder, is that of the gas that exists directly above a liquid. So that's going to be the, we'll draw it on this side, the pressure of the vapor directly here as the gas begins to collect above the surface of a liquid. The significance of this vapor pressure reaching 1 atmosphere of pressure means that we have now such an abundance of particles present due to the increasing temperature and the increasing kinetic motion of these particles that the gases that exist above the liquid can no longer tell the difference between existing above the liquid and that of the ambient conditions above the beaker. Therefore, the gaseous particles and all of their new kinetic motion are going to escape and leave. So this is the phenomenon that we see as boiling. Once a liquid begins to bubble, the bubbling occurs because there's so much kinetic motion that the particles are going to now gain equilibrium with the ambient pressure and are just going to bubble away and escape to go join the atmosphere whose pressure they now match. So this definition is true no matter what liquid we are observing. The temperature at which this vapor pressure right here equals 1 atmosphere is going to be equal to our boiling point. And so in the graph down below, we can see that there are a series of liquids that are being, their vapor pressures as a function of temperature are being listed here. Diethyl ether, or just ether for short, bromine, ethanol, water. So we'll kind of outline this blue one here, octane, and ethylene glycol. Okay, so each of these liquids we can see with a different color here. So orange, red, green, blue, yellow, and purple corresponding to the key on the right. Now this blue, again, corresponds to our water. So we can see that the vapor pressure in millimeters of mercury as a function of temperature for water steadily increases. So the vapor pressure is initially very, very low at cold temperatures. And as we begin to increase this, we can see somewhere around room temperature, the pressure is still very, very low, definitely less than that of 1 atmosphere. And it's not until we get up here, which is where we are at 760 millimeters of mercury, which is again equal to 1 atmosphere, that we can see that, or that we would conclude that the liquid is going to boil. Now the temperature that this happens at for water, we can trace all the way down and see that this is 100 degrees Celsius, which is what we commonly know to be the boiling point of water. All right, so this is why water boils at 100 degrees Celsius. There's nothing magical about 100 degrees C. It just so happens to be the temperature that the vapor pressure of our water, the vapor pressure again right up here above our beaker of water, equals that of the ambient atmosphere. All right, so all of the surrounding liquids, we can make similar conclusions to determine where their boiling points are. For diethyl ether, for instance, this orange curve, at the same ambient pressure, for the vapor pressure, we trace our way down here and we can see that the boiling point is somewhere, it looks like around 30 degrees Celsius, which makes sense because diethyl ether is very, very volatile and even with very little prompting is going to start boiling and the liquid will start evaporating away. In contrast, another compound, which we can see the intercept of 1 atmosphere for vapor pressure here on this purple curve, the ethylene glycol, has a very, very high boiling point at around 200 degrees Celsius. So this is double that of water. Now the reason why each of these liquids vary in terms of their normal boiling point pertains to what intermolecular forces are present inside of the liquid, right? What intermolecular forces are present between each of the molecules. So not only do the liquid properties like surface tension and volatility and viscosity pertain to intermolecular forces, but the phase change capabilities of these materials are going to depend on the intermolecular forces as well. So how do we quantify the energy necessary to actually get our liquid to boil? Well, this we call the enthalpy of vaporization. So this is just another special enthalpy, just like all of the other previous enthalpies we've discussed starting in chapter 10. But just like I said in chapter 10, there is nothing so special about these enthalpies that they require special treatment. So this enthalpy of vaporization, or this delta H with a sub vape, we're going to treat in the exact same way as all of the previous enthalpies, so we can write out equations like Q is equal to N delta H of vaporization. So the Q in this equation is just the same kind of heat that we have worked with before, where it could be positive or it could be negative, all depending on the direction of the heat. Is it going into the substance or out of the substance? The N here is going to be the number of moles, and our delta H of vaporization is the heat required to transform 1 mole of a liquid to a gas. So this is going to represent how much energy we need to put in to actually get that liquid to turn into a gaseous particle. All right, so let's get some review, right? It's been a while since we've worked maybe explicitly with this kind of equation. So let's determine how much heat is required to vaporize 9.11 grams of acetone. So this is the amount of acetone that you might find in a bottle of fingernail polish remover. So if we wanted to vaporize all of this, how much energy would we have to put in at its boiling point? All right, so here we have the chemical formula of acetone. We are also told what the enthalpy of vaporization for acetone is, which is 29.1 kilojoules per mole. All right, so I'm gonna let you guys just kind of like dust off those brains, work through this problem, and see how much heat, how much Q is necessary or required to vaporize this acetone. Okay, so when solving this problem, there's one of two ways that you can go about it. If you're more of an equations person, we can use the equation that we just learned, which is another form of the same equation that we've been seeing since chapter 10. Q is equal to N times delta H. Specifically here, we are working with the enthalpy of vaporization. But again, if you didn't explicitly include that subscript, if you just kind of ignore this vaporization here, our equation Q is equal to N delta H is the same equation we've seen for a couple of weeks now. All right, so all we need to do is figure out how many moles of material we're working with and what our enthalpy is. We are also not told in the problem exactly what unit Q should be in, so it could be in kilojoules, it could be in joules. We don't really have to worry about converting here. All right, so we need number of moles. Well, we can see we're not explicitly given a number of moles, but we are given a mass in grams as well as a chemical formula. So this means we can find N by taking 9.11 grams and multiplying it by the molar mass of our acetone. The molar mass of acetone is going to be 58.077 grams per every 1 mole. So this all here is equal to our N. Now I'm not going to explicitly calculate what this value is. I'm just going to let this represent, in combination, the product of this is going to represent N inside of our chemical equation, and our delta H is specifically told to us, 29.1 kilojoules per every 1 mole. All right, and the reason why I'm writing it like this, with the 1 mole specifically being present in the denominator, is because this is the second way that we could solve our problem. Even if you don't remember the equation here, N times delta H, we can still use the units to figure out how much heat is required, because we can see that we're given grams in the problem. We can very easily figure out what the molar mass of this is to get into moles, because we can see that we have a number that is present in the units of kilojoules per mole. So if we get into the mole, we can easily jump out of the mole, and our final answer will be in kilojoules here. So either way, we can pretty easily see if you're using an equation or if you're using dimensional analysis, you're going to get to the same answer, assuming that your units are canceling out properly. So the final answer for how much heat is required is 4.56 kilojoules. All right, so hopefully that felt more like review as opposed to something totally brand new. If it does feel brand new, I would recommend going back and checking out some more of those Chapter 10 enthalpy problems just to dust off those old skills. But there are more phase transitions than just liquid to gas, right? That's just one of the transitions that we can make. So what we're going to do now is talk about another phase transition, this being that of our melting point. The melting point, by definition, is the temperature at which a solid transforms into a liquid. We could come up with the same type of graph as what we saw in the normal boiling point slide, but You guys get the picture, right? We're looking for the temperature here at which the solid is going to begin transforming into a liquid. The enthalpy that corresponds to this transformation is known as the enthalpy of fusion. So the enthalpy of fusion is going to be the heat required to transform 1 mole of a solid into a liquid. All right, we can see the equation presented here. Q is equal to N delta H of fusion is the exact same setup. It is still a Q is equal to N delta H. And we're going to use this equation in the exact same way as what we used the previous equation. The only difference here is that the delta H is going to correspond to the fusion. Now the enthalpy of vaporization for a particular substance is not going to equal the enthalpy of fusion. So it's going to take more or less energy, all depending on your substance, to get something to turn from solid to liquid as opposed to liquid to gas. So for this reason, it's going to be important to, like if you're looking up a value, let's say for these enthalpies, specify what enthalpy you are working with. Is it vaporization or is it fusion? Because these two numbers recorded in some table are going to end up being different, and not just because of the units, right? The energy requirement is going to be different as well. So a material can go from liquid to gas, it can go from solid to liquid, and as we saw with carbon dioxide and its phase diagram, a material can go from solid to gas as well, just totally skipping over the liquid phase. This we call the sublimation point, the temperature at which a solid is going to transform directly into a gas. Now, most materials, at least most common materials, do have a sublimation point. They just aren't at ambient pressures, like 1 atmosphere of pressure. Carbon dioxide is a very special material, where in its solid form, it just looks like this hunk of white frosty stuff that we commonly refer to as dry ice. And we call it dry ice specifically because there is no liquid present, right? Again, there is no liquid carbon dioxide. This ice, quote unquote ice, is perfectly dry. And the dry ice itself, just sitting on a desktop at room temperature, we would see some like frosty or like hazy condensate kind of like evaporating off. We would see the product of sublimation of the gaseous CO2 coming directly off of the dry ice, like so. There is an energy requirement to go from solid to gas, like even if it just spontaneously happens, like with dry ice, the ambient temperature, right, room temperature is enough or is hot enough to supply the heat requirement to get this transformation to occur. Sometimes we have to put in even extra energy, and the amount of energy we have to put in is known as the enthalpy of sublimation. This is the heat required to transform 1 mole of solid to gas. So again, we're just totally jumping over the liquid state. The equation, straightforwardly, that we would need to find the amount of heat Q required to transform a certain number of moles N from solid straight into gas, we can see here, as I have boxed it, Q is equal to N delta H of sublimation. However, we normally don't keep recorded tables of sublimation enthalpies. And the reason why is mathematically, and according to Hess's law, as it turns out, the enthalpy of sublimation is equal to the sum of the enthalpy of vaporization and the enthalpy of fusion. So we can explain this again using Hess's law. According to Hess's law, if we add up 2 reactions together, if we add up 2 reactions, we can add their enthalpies. So if we consider the hypothetical reaction of taking, let's say, solid carbon dioxide and turning it into liquid carbon dioxide, and then in a second process, taking that liquid carbon dioxide and turning it into gaseous carbon dioxide, well, the first reaction's enthalpy would correspond to an enthalpy of fusion, and the second reaction's enthalpy would correspond to an enthalpy of vaporization. If we add these 2 reactions together, what we would find is that the carbon dioxide in liquid state is going to cancel out, giving us something that looks like carbon dioxide solid is moving directly into carbon dioxide gas. Well, if we added these 2 reactions together, again, according to Hess's law, we're going to add up these 2 enthalpies together, and this is why our enthalpy of sublimation, energetically speaking, is equal to the sum of our enthalpies of vaporization and fusion, even if physically the material itself does not transform into a liquid in between the transformations of solid to gas. So the takeaway message on this is if you need to find an enthalpy of sublimation, either in the textbook or if you're just Googling it, and you can't seem to find an explicit value for an enthalpy of sublimation, try looking up the enthalpies of vaporization and fusion instead. The sum of these two enthalpies is going to give you your enthalpy of sublimation, thanks to Hess's law. Now we've been looking at these transformations in one given direction, right from the condensed phase into the less condensed phase. So we've been looking at melting, we've been looking at boiling, we've been looking at sublimation in the process of going from left to right in this diagram. Insofar, we have learned about the enthalpy of fusion corresponding to melting, the enthalpy of sublimation corresponding to subliming, and the enthalpy of vaporization corresponding to boiling. But what about the phase transitions in reverse, right? What do we call gas turning into liquid? What do we call liquid turning into solid? And specific, like even more than that, what do we call gases condensing straight down into solid form? Well, in the reverse direction, we refer to these processes by different names. So we can see gas turning into liquid here is labeled as condensation. As liquid turns into solid, we commonly refer to this process as freezing. This is also true no matter the material. And last but not least, and probably the least familiar to people, is that a gas turning directly into a solid is known as deposition. The reason why we call the process deposition is because we are taking a series of separate particles, and we tend to, just like with condensation, adhere them directly to another surface, or they will hyper condense down into a very tight solid form. So we are depositing the gas into the solid state. Because these processes are exactly opposite of those that we've already talked about, all we need to do is consider Hess's law to figure out what the corresponding enthalpies of these processes are. For instance, a liquid turning into a gas is known as boiling, and it has a particular recorded enthalpy of vaporization. Well, the same gas turning into a liquid is just the reverse of the first reaction. Therefore, an enthalpy corresponding to condensation is just the negative enthalpy of vaporization. Similarly, when you take a liquid and turn it into a solid, since this is just the opposite of melting, the corresponding enthalpy is going to be the negative enthalpy of fusion. And last but not least, if we're taking a gas and turning it into a solid, what we are doing is the opposite of sublimation, and therefore the enthalpy or energy requirement is going to be the negative enthalpy of sublimation. So for this reason, if you're ever looking up enthalpy values, again, if you're ever Googling them or just looking them up in your textbook and you're like, I can't find an enthalpy of freezing, or I can't seem to find an enthalpy of condensation, the reason why is we only need to record the values numerically once, and if your reaction is going in the opposite direction, all you need to do is toss a negative sign onto your enthalpy according to Hess's law, and you are golden. The addition of this negative sign also adheres to our previous conversations of what it means to be exo versus endothermic. An exothermic process is one in chemistry that is considered to be negative because energy is leaving your system. This we've already talked about before in chapter 10, but these enthalpies also adhere to that because, for instance, if we take a gas and condense it down into a liquid, energy needs to leave the gas in order to enter a liquid state. This matches our negative enthalpy of vaporization. This process is exothermic, the energy is leaving, and the enthalpy will be negative to correspond to that. Any process with which energy is going into your system is going to be positive, this endothermic process. And for instance, an enthalpy of fusion is going to have a positive value because we're putting energy into the system to go from solid to liquid. So anytime on this type of diagram we're going from left to right, our enthalpies will be positive because we have to put energy in. Anytime we move from right to left, our enthalpy should be negative because we are releasing energy into the surroundings. The last thing that we need to talk about today is what is known as a heating curve. The reason why we need to talk about this is thus far we've only talked about or addressed, Q is equal to N delta H, the amount of energy required to be put into a system or taken out of a system as it changes phase. However, as we have already learned about in chapter 10, there is another, let's say, instance with which we need to calculate a heat change, and this is when we are changing the temperature of our substance. And our equation looked a little bit like Q is equal to SM delta T, where again, specifically, we're looking at the temperature dependence of our substance and how the heat is going to change as a function of changing temperature. All right, so in the heating curve, we are now taking into account both of these possibilities, the heat going in or coming out of our system, not only as we change phase, but also as we change temperature. All right, so by technical definition, our heating curve is a cross-section of a phase diagram at some constant pressure. It doesn't always have to be ambient pressure, but that's normally when it is. And specifically what we are plotting is the change in temperature of a material as a function of energy, aka as a function of Q. So let's turn our attention to another phase diagram, which we can see down here on the left. This is the phase diagram of water. We can see that there are 3 different regions that are labeled here. We have the solid ice, we have the liquid water, as well as the gaseous water vapor. So these 3 phases are in similar locations as the carbon dioxide's phase diagram that we've seen before. There's also the triple point that is labeled here, as well as the critical point. So again, common features of a phase diagram is to point out where either all 3 of your phases can coexist, or when the new critical fluid phase becomes introduced at very high temperatures and high pressures. All right, so what we're going to do is pick a constant pressure and draw a horizontal line across this phase diagram. And the pressure we're going to pick out first is going to be that of ambient pressures. And notice that our pressure axis here is in kilopascals, not atmospheres. 101 kilopascals is approximately equal to 1 atmosphere, so this is going to be where we consider ambient conditions to exist. So let's take a cross section of this phase diagram by drawing a horizontal line. All right, did a pretty good job there. Horizontal line across our phase diagram. So what a heating curve does is observes how the temperature changes across these phases and how energy is going to be mapped as a result. All right, so what we're going to do is pass through the regions of this phase diagram and connect them to the heating curve present here on the right, because that's what this illustration is on the right, is that of our heating curve. All right, so we're just going to move along with the heating curve, where we can see in the lower left we have something labeled as heating the solid. So we're going to also start in the solid phase somewhere here on our phase diagram. So let's just say the most extreme, the most leftmost section of this phase diagram. All right, well, in order to get from solid to gas, because again, that seems to be what's happening here in our heating curve, we have heating solid in the lower left, heating gas in the upper right. We are similarly going to move to the right on our phase diagram, moving out of the solid and ultimately into the gas. All right, so as we start moving through our phase diagram, we can see that we are increasing the temperature, right? That's what's happening as we're moving to the right here. We are increasing our T inside of the phase of being a solid. This is going to correspond to this first section here on our heating curve, where the temperature is increasing as well as our energy is increasing. So the first section of this heating curve is going to get us up to the melting point of our material, and in this case, again, we're working with solid ice. All right, so before we actually get to the process of melting, what we first need to recognize is that in this first section that is labeled with this kind of blue diagonal, we increase our temperature and we increase our energy. There is a positive correlation here. And the amount of energy specifically that is going to be necessary to heat up our solid from whatever temperature it's at, right? We'll just say that this is temperature T. In order to get this thing up to its melting point, we're going to have to put in energy that is equal to the specific heat of the material times the mass of the material times the temperature change of the material. All right, so we're looking at associations here. Temperature versus energy is the association on our heating curve, and we're going to have to put in an amount of energy such that we get up to the melting point, which I have now kind of dotted here on our phase diagram. Now the melting point for water we know is 0 degrees Celsius, hence the 0 intercept here. So on our heating curve, this temperature intercept right here is also 0 degrees C because we're working with water. Now what's pretty awesome is we can see that as we continue to put in energy to melt our solid ice, the temperature does not change, right? It's a flat line, meaning that temperature remains constant. This is true on the phase diagram as well. The process of melting only takes place at 0 degrees Celsius, and the phase diagram makes it look like the process happens like that, right? It just goes straight from solid to liquid, and there's no mention of time or energy transfer, but that's the purpose of the heating curve. The heating curve illustrates how much energy needs to be put in to actually get this specific mass of stuff from our solid into the liquid. So as we are undergoing this melting process, the amount of heat that is required, our Q, that is required to get from solid to liquid is going to be equal to N times our delta H of fusion, right? So now we're starting to plug in our equations that we've learned so far and kind of figure out visually what they represent. So in this heating curve, ultimately what we're trying to map is Q. This is our energy is Q. There's just different ways that we can calculate it, all depending on whether or not we are changing phase or changing temperature. All right, but once we have undergone the melting process, everything is totally melted, we can start now heating our liquid. So this is now the next section of our heating curve. We are currently heating the liquid, and on our phase diagram, what this means is that we are approximately somewhere in here. And we can see there's a pretty long process with which we can heat our liquid, and we're going to keep doing so by increasing our temperature again. Right, so in this phase diagram, we can now clearly see that we are going from 0 degrees Celsius up to the next point with a phase boundary, which is going to be 100 degrees Celsius. On our heating curve, we are going from this 0 degrees intercept up to here, which is, there we go, drawing the line across, a 100 degree Celsius intercept. In the process of heating our liquid, since we are changing temperature again, we are going to be able to find the exact amount of heat necessary for this process by taking again our specific heat of the material, multiplying it by the mass of the material, and multiplying it by our change in temperature. And our heat will continue to vary as a function of temperature up until we get to the boiling point at 100 degrees Celsius, where on our phase diagram, now here we can see we're at the next phase boundary. Temperature will not change as we go from liquid to gas, and that is represented in our phase boundary again by having this one intercept between the liquid and the gaseous boundary. 100 degrees Celsius will be the temperature of our material as it undergoes the process of boiling. Now the process of boiling and the amount of heat necessary to undergo boiling, we've also just introduced this equation today. Q is equal to N times delta H of vaporization. So this is going to be useful to us to calculate exactly how much heat is going to need to be put into the system to get from our liquid state to our gaseous state, which again will be at 100 degrees Celsius. Now once we've boiled all of our liquid into gas, the heating of the gaseous phase can now begin as we exit or cross through this phase boundary in our phase diagram, and now we're somewhere here on the right, where again our temperature can begin to increase again. We have transitioned into a totally new phase, and we can increase our temperature as high as we are able to go up until we get to this critical fluid or critical point stage. All right, so the heating of the gas is going to correspond, or like to find the heat associated with this transformation, the energy associated with this transformation. This will be another instance where we use Sm delta T, where heat is varying as a function of temperature. Well, when would this type of problem be useful? Well, it depends on what kind of question we're being asked, but normally the type of question is how much heat is required to get from one temperature of one phase to another temperature in another phase. So let's say specifically, I asked you, you're starting with solid ice around here. like let's say this is just by looking at the intercept, somewhere around negative 0.5 degrees Celsius, hypothetically. And I asked you, well, how much heat would you need to put into the system to get this to turn into a liquid at 50 degrees Celsius? Well, there are 3 different calculations that you would need to take into consideration. The first is the amount of energy that you need to put in as a function of temperature to get up to the melting point. The second would be how much energy is it going to take to actually cross through this boundary condition, this phase transition, to get to the liquid water phase. And then last but not least, how much energy do you need to put in to transform your temperature again from 0 degrees Celsius up to 50 degrees Celsius. So these are the types of problems we're going to be looking at. As you go from one phase to another phase, and as you're changing temperature in addition to that, how much total energy is necessary to either heat up your material, or conversely, we can always go in the opposite direction, how much heat needs to be taken out from your material to solidify it. So let's calculate just that type of problem. Let's find how much energy in kilojoules must be absorbed by 1 gram of water in order to heat our sample from negative 5 degrees Celsius all the way up to 110 degrees Celsius. So this is going to be the most extreme form of this problem, where we are going from something in the solid phase, because this is water, and we know that below 0, water is going to be a solid. So we're going from solid all the way up to gas. And even more than that, we are going to need to pass through our phase boundaries. So I'm gonna give you guys the chance to kind of work through this problem and absorb, pun intended, what we have talked about thus far. But then when we come back together, we can see how we can simplify these equations, simplify our approach, and figure out how much energy is necessary for this transformation. Before you start working on the problem though, there is some information I should probably give you, which is that of the enthalpy of fusion and the enthalpy of vaporization for water, since that's what we are working with. The enthalpy of fusion for water is 6.01 kilojoules per mole, and the enthalpy of vaporization for water is 40.65 kilojoules per mole. All right, now you have the information you need to work through the problem, or at least get it started. Definitely feel free to try and finish the entire thing before unpausing the video, but when you unpause, we will come back together and solve this all together. All right, welcome back. You had the information you needed, so let's come back together and solve for the amount of energy necessary to get our solid water, our solid ice, into gaseous steam. All right, so there are 3 different sections of the heating curve that we're gonna have to pay attention to. The first is our temperature change, right? We're going from negative 5 degrees Celsius up to 110 degrees Celsius. The second is we are going to be melting our material, so we need to pay attention to how much energy we put into phase transition there, as well as we're going to be boiling our material. So because we have 3 different let's say heating portions that we need to concern ourselves with, I'm going to label the first as the calculation for Q1, the second as our calculation for Q2, and our third as calculation for Q3. So let's start with Q1. Q1 corresponds to the energy of our temperature change. So this is going to be our Q is equal to SM delta T. Now you may ask yourself, are we allowed to consider negative 5 degrees Celsius, our T1 or Ti, our initial T, and 110 degrees Celsius as our TF, even though we are crossing through different phases in between these extreme temperatures, right? If we were to go back to our heating curve, the melting of the solid, the melting of the liquid, the melting of the gas, were separated like this, where there were 2 different phases in between, the phases of melting and the phase change of boiling. Well, even though there are some melting and boiling processes in between these temperature changes, we are still allowed to use negative 5 as Ti and 110 as TF. because we are going to be calculating the heat exchange of the melting and boiling separately, we can sort of pull out these other sections and calculate our Q2 and our Q3 separately, right? That's literally what we're doing here, is we're considering the processes of melting and boiling in different calculations. So all we need to do is, because the slopes of these lines are the same, kind of tack together our initial condition, our Ti is equal to -5 degrees Celsius, and our final Tf of 110 degrees Celsius, and say that the temperature change in between was a linear exchange, and therefore we only need one Q1 calculation. Now you can definitely prove this algebraically, and if you wanted to do that, feel free. If you're comfortable with the math, you could also solve for the Q for each of these individual temperature exchanges, because we know that the boiling or the melting point of water is 0 degrees Celsius and the boiling point is 100 degrees Celsius. But that's going to be an exercise I leave to the reader. Just if you don't want to go through that process, trust me in that the dependence of energy on temperature is linear. Therefore, we only need to consider our most extreme Tf and our most extreme Ti. So with that knowledge, let's plug in our specific heat for water, which is 4.184 joules per gram degree Celsius. Our mass for the water, which is 1.0 grams. And our extreme temperature difference here, our final T being 110 degrees Celsius, and our initial T at being a -5 degrees Celsius. So we are going to subtract out a negative here, which means that we are going to ultimately be adding a number. And this is good because we are going from solid to gas, right? We have to put energy into the system, and we know that we want our Q to be positive, right? Energy is being absorbed, which means our final answer should be a positive answer. And the math, if we're plugging things in correctly, will work out for itself. This gives us a temperature change, or not temperature, sorry, an energy change of 481 joules. All right, so with 481 joules corresponding to our Q1, let's turn our attention to Q2 and Q3. Now we will have to calculate Q2 and Q3 differently. We can't combine them into one big thing like how we did with our temperature change, because our enthalpies of fusion and vaporization are different. Our enthalpy of fusion will be necessary when solving for the heat exchange for melting, so our Q is equal to N delta H of fusion in this case. Now the number of moles of water is not explicitly given to us, but we can always use dimensional analysis and take our mass times the molar mass of water, which there is 1 mole per every 18.02 grams. And again, we can use the periodic table to find numbers like this. And we'll multiply this by our enthalpy of fusion, which is 6.01 kilojoules per every mole. All right, we crunch these numbers, finding that grams cancel out, moles cancel out. Our final answer will be in kilojoules in this case, not in joules, which is okay for now. Our answer here being 0.33 kilojoules of heat needed to melt this 1 gram of ice. Last but not least, we are going to need our enthalpy of vaporization. I just realized my little lines to draw attention here look like negative signs. They're not negatives, they were just little dashes to marker things. I'll turn them into arrows now for clarity. We're going to use our enthalpy of vaporization to solve for Q3, which is also going to be equal to N times delta H, in this case, vaporization. All right, so our 1 gram is going to be, again, turned into moles using our molar mass, which is 1 mole per every 18.02 grams. And here, now we insert our 40.65 kilojoules per every mole to find a total number of kilograms equal to 2.3, or not kilograms, kilojoules of heat needed to be inserted into this liquid gram, or this liquid water, this 1 gram of liquid water, to turn it into a gas. All right, so our last but not least, now that we have found how much heat is necessary to change the temperature, how much heat is necessary to melt, and how much heat is necessary to boil, all we need to do is add these things together. Our final answer should be in kilojoules according to the problem, which means we are going to turn this 481 joules into kilojoules by dividing by 1000. So this will be equal to 0.481 kilojoules. And now we have everything in the same unit, and we can add everything together. So our final answer is going to be 3.11 kilojoules of energy necessary to take this -5-degree 1 gram ice cube and turn it into steam at 110 degrees Celsius. And that is what I have for you guys today. So if you would like some extra practice with phase changes and or our phase diagrams, please check out the textbook, which we can see the problems here, 12.51 and 12.52, both correspond to phase changes. If you have any homework, please double check and do your homework. If you have any questions, please do not hesitate to ask. And class is dismissed.